Hello, my name is Blair Geip, and today I'm going to be talking about aerodynamics and how they play into NASCAR. Here's an overview of what I will be talking about today, which includes downforce, drag, and car design. In NASCAR, aerodynamics play a huge role in how fast and safely cars can travel at speeds exceeding 180 miles per hour. The three main components of aerodynamics include downforce, drag, and car design, which determine how a race car interacts with the environment around it, including the air and ground. Understanding these components behind the forces explains why certain car designs and racing strategies are so much more effective than others. Downforce is the aerodynamic force that pushes a car downward onto the track. It is created when air flows over the car's surfaces in a way that creates negative lift. It increases traction, allowing the car to corner faster without losing grip. And then we have drag, which is the force of air resistance that opposes a car's motion. As a car moves forward, it must push air molecules out of the way, creating a resistive force. Drag increases rapidly with the speed and limits the car's maximum velocity. So the engineers of NASCAR have to work to minimize drag while still maintaining enough downforce for stability. Drafting, also called streaming, occurs when one car follows closely behind another and enters its low-pressure wake. The trailing car experiences significantly less drag and therefore requires less power to maintain those high speeds. All of these components show how the physics of airflow, pressure differences, and force balance, shape the design and behavior of NASCAR race cars. Okay, now we're going to be talking about downforce and drag equations. Both of these equations look very differently, or look very similar, but I'm going to be talking about downforce first. So 1/2 rho is simplified to a constant value of 0.00119. And that is due to air density, which changes due to elevation, temperature, and humidity. We're going to be using this static value consistently because it is the average of all environment. A in this case is the area of the wing in square feet. CL is the coefficient of lift. It's very difficult to come to one value because it changes with different shapes of wings, how fast the car is going, the wing angle, and turbulence. For the time being, we're going to be using a value of 1. And then we have velocity squared. And we need to know that 1 mile per hour is equivalent to 1.467 feet per second. The average area of a wing in NASCAR is 1.5 to 3 square feet. So we'll be using 2.25 square feet as our area. The average speed of a car in NASCAR is 188 miles per hour. So when we put this into the equation, we get 204. But what does that really mean? It means that 204 pounds of push-down pressure is occurring. That force increases the car's grip on the track. This extra force gives the tires more traction, helping the car corner faster without sliding. In NASCAR, drag is air resistant that slows cars down. So it's crucial that engineers minimize this through streamlined designs. The NASCAR drag equation uses the standard aerodynamic formula, where we have D as drag force, rho is air density, B is velocity, CD is the drag coefficient, or shape and efficiency, and A is the car's frontal area in square feet. This formula calculates the resistance air puts on the car, which is a crucial factor in NASCAR for managing speed, fuel, and drafting, with engineers constantly tweaking the car's shape, which is CD, and size, which is A, to find the optimal balance between drag and downforce. The average frontal area of a NASCAR car is 23.7 square feet, so we'll be using that. And then the average drag force coefficient is 0.45 to 0.5, and we will be using 0.5. That means that at 188 miles per hour, the air is pushing backwards on the car with 1,072 pound weights resisting its motion. That's over half a ton of force trying to slow the car down. The engine must constantly overcome this force just to maintain speed. This is why aerodynamics matters so much. A tiny reduction in CD or frontal area could save hundreds of pounds of drag, increasing speed and reducing fuel use. Drafting helps because when a car sits in another car's wake just behind them, that drag force drops dramatically, allowing higher speeds with less power. Now we're going to be talking about car design. NASCAR cars are engineered to manipulate airflow for maximum downforce and minimum drag. The shape of the car determines how efficiently it cuts through the air. The front splitter creates high pressure on the front end. It adds front downforce for stability in turns. The rear spoiler, or the wing, increases rear downforce by redirecting airflow upwards. This prevents the back wheels from losing traction. The overall car body shape and smooth surfaces reduce drag, which lower CD. The curved roof and tapered rear minimize turbulence. The underbody airflow. This low pressure region beneath the car generates additional downforce. Here we have some of the older NASCAR car, and then we have a new NASCAR car. You can see the difference, especially in the spoiler, and you can see in the under area of the body. Aerodynamics play a huge role in NASCAR performance, with downforce, drag, and car design working together to determine how fast and stable a car can be. Downforce provides the necessary grip for high-speed cornering, while minimizing drag allows drivers to maintain top speeds on straightaways. The shape of the car, its spoiler, body contour, and frontal area is engineered to balance those two opposing forces. Precise aerodynamic tuning and strategic drafting, NASCAR teams are able to optimize airflow to gain speed, improve handling, and enhance safety. Ultimately, the physics of air resistance and lift define how a race car performs on the track, making aerodynamics one of the most important aspects of modern NASCAR engineering.